Hello. How you doing? All right, all right. How's everyone hanging? How's everyone? How you guys hanging? What you guys doing? Let's see. Let me get my notes here. Okay, here it is. Yeah. What's this? All right, all right. Oh yeah, yeah. That's what this is. Excuse me. So you can guys see everything? Like, can you see the paper? You're ready to learn about triangles. Triangles. Okay. Okay, so a triangle is something with 3 vertices and 3 edges. Yes, that's a triangle. Well, if I need more paper, I know where to get some. All right, guys. Today, you know what we're doing, and you know why you're here. So, okay, how should I start this? So guys, you know a little bit something. One of the things that we have is a thing called what's it called again? I actually have a note. So it's called, is it right here? Shit. What's it called again? Okay, ignore that. All right, so does everyone know what an electrode is? An electrode. All right. So an electrode is essentially like it's like a metal. It's like a conductor that's meeting with some kind of dielectric. So, like a capacitor, when you have like a capacitor that is like this, like 2 little metal thingies, and for a very brief amount of time, you have current flowing through it. So, like these parts right here, these are electrodes, and the space in between is a dielectric. And this is important because this is a precursor to the idea of an anode and a cathode. So we have essentially the anode and the cathode are 2 electrodes that are doing something, and that something makes them become a electrode and a cathode. Anode and a cathode. So what is an anode? An anode, let's say we have some zinc. We got some ZN, a zinc metal, and it's like in some liquid, and it's connected to something. Who knows? Who cares? So the reason why, what makes this an anode is essentially the flow of current going into it, and it's usually coming out of the thing called the cathode. The cathode. So we have another piece of metal right here, probably in the same liquid, and current comes out of the cathode into the anode. Now, in this configuration, the current is flow of positive charge, and so it's essentially the direct. We want to know where the electrons are going. This is important for triodes. This is really important. So we're going to call the little electrons little e with a minus sign. This is an electron. So we like electrons because they're cool. So electrons are flowing out of this thing's called the anode. Actually, let's put this should be called the anode, the cathode. So we have electrons coming out of the anode, and their electrons are headed towards the cathode. But what's more important is the flow of current. Now, in a situation where we have like the flow of current going the other way, say that instead of like this, say that we have current flowing, the new current, but it's flowing this way. Current that flows this way. So that, what does that mean? What that means, the E's, the little electrons, they're going the other way now. So now we have electrons, but they're going this way. They're coming out of this piece of metal. And if for whatever reason, whatever biases this circuit, so that current flows in the opposite direction, the role of anode and cathode shifts. They change. So the anode becomes the cathode, and the cathode is now the anode. Yay. So here's the thing. That doesn't work. That's not how it works with diodes. Like diodes just are a different kind of animal. So do you guys remember, or do you guys know what a diode is good for? What's the point of a diode? So, first of all, do you know why it's called a diode? Can you see anything back here? Okay. Actually, we'll call this page 1, and call this page 2. So here's the deal. A diode, one of the things it's called a diode. Now, it's different from a capacitor. A capacitor stores stores energy in an electric field. So what we have there is a diode that doesn't do that, but it still has 2 electrodes. And that's why it's called a diode, because it has 2 electrodes. But a capacitor is different, though, because a capacitor does a different function. So we have a diode, and the point of the diode is that we want it to have current flowing one way. So current only one way. So we only have one current going in one direction. And so in this configuration, so we have right here, this thing right here. So maybe this has a filament too. So this right here is the cathode. We're going to call this the cathode. And this right here is called the anode. So, but the thing is that you might think, okay, so electrons, so let's go back to the other page. So in the anode, current flows out, and current flows in, and the electrons go out. So in the anode, so here surely the current flows out. Wait, does it? I may mix them up. So you would say the current flows in. Okay, so you would think the current. You would think that, let's mark this with the green. Let's use the green one. So you would imagine that the current I goes in, right? Well, here's the thing. That's not true. Because right here is ground. Maybe there's something in between, but yeah, there's ground. This is ground, and this circle is what we use to indicate that this is a tube. This is a diode, and a diode is inside a tube. Boom. Now, so why is this called the anode and why is this called the cathode? It's a little phenomena that's, we're going to call it something called forward bias. So for the functions of diodes and triodes, in vacuum tubes, we're going to refer to this as forward biased. And this is important because it doesn't follow the conventions of what an anode and a cathode does. So, and why do they do this? I'm not sure. It has to do with like the history of the devices and why they came to be. Faraday called it the anode and the cathode for some weird messed up reason. Maybe he was on drugs. But the guy who made, well, actually I don't know. No, not the guy. The people who may have made the diode kind of had a different idea. And so for the tetrode, we're going to call the thing that's connected to the ground, we're going to call this the cathode. And what we need to know is that electrons go out of the cathode and the anode collects the electrons. So therefore, current goes that way. So it's kind of like the opposite. And this is just some weird, messed up history naming convention. That's how I see it. I'm pretty sure there's a good reason, but who knows what it is. So now we get to the good part, the great part, the excellent part. So now what we want to do is we get to page 3. We get to the triode. Now this is it. So so when we get to the triode, someone decided like, a diode's cool, but you know what? We want to do more things. And we also want to be awesome and amazing. So someone had the bright idea to decide, what if we could like control the flow of the electrons? Let's say we could increase it or decrease it or something like that. Do it for some reason. Like how can we like adjust it? So, one would you think that? Actually, hang on. What's this? So, we want to know why. Like, how could we do it? How could we control the electrons, and how can we make the electrons change the flow, change the rate of the electrons? Do you guys have any idea? Any idea? So, like, if we can control the flow of electrons, we can like control how like what we can control a lot. Like this leads to new possibilities of like how we can like add more complexity and usefulness towards our electronics. Oh, so you said magnets? You're crazy. You're like insane. Magnets. The magnets are like okay. So magnets aren't going to do anything for us in this regard. I mean, it's not a bad answer, but like, no, it's not the answer. So now, here's the thing. So we want to know, what kind of like what if we like introduce like electrons that like cannot be like changed, that cannot be biased. That, let's say we could somehow like introduce electrons. Say we had the anode and we have the cathode. So like electrons flow this way, but what if we could introduce some sort of what if we could like introduce some kind of alternative where like say that if we could somehow introduce electrons here, what would that do? That would stop the flow of electrons or interrupt it. So because like electrons, they don't like each other because you know the guy, the XMDI said that magnets, and maybe the idea was there is that we could polarize, like introduce a polarization in the flow of electrons to disrupt their flow. So how can we introduce electrons here? And now, you know, maybe we could, you know, we don't want to mess with protons. Don't mess with protons. So how do we like put electrons in here? How do we like do that? You know, maybe we could put some kind of a piece of metal in here that allows electrons to flow through. And if we like negatively charge it, like maybe if we like maybe if we get like a battery and the negative part of the battery somehow influences something right here where so there's little holes where electrons can still flow through, but if we like charge this really negatively, so that say that like say this the voltage here is like -3 volts and this here is 0 volts, so like electrons really won't like this. A very small syringe. That's a good idea. But that's not what happened. They didn't do that. Well, this guy didn't do it. So the idea here is that so one of the things that some guy, he was a genius. This guy I'm about to mention, he was a complete genius, probably a genius, but he was kind of messed up in his own way. So the guy that I'm talking about is a man named Lee D. Forrest. Now this guy is the man. He made things awesome. Well, I'm actually, this guy's kind of important. Well, he did this important thing. This is probably the best things ever. He actually probably did a lot of stuff, but I mean, like, this is really, really important. This is really important. So he is credited for inventing. Actually, he's credited for inventing the electronic amp, or the first practical electronic amp. Not the first electronic amp, the first practical one. So, if you change things if you change the way you say something, you can make something that's so totally insignificant seem super important. So he made the triode in 1906. And here's what he did. So he got 3 electrodes. So he inserted an electrode in between the cathode and the anode, and it has the capabilities of allowing electrons to flow through to the from the cathode to the anode, and that's like the biggest, awesomest thing. As like one of the craziest things. Is awesome. This is so cool and so awesome it's like it's not as good as discovering alternative current, but this is still pretty good. So here's how we show it. So we have our anode, we have our like what should I say? Yeah. We have the cathode. So now what we have is this little thing, and we're going to call this the grid. And actually, why is it called the grid? Let's see, why is it called the grid? Look at my notes. Yeah, I'm not sure why it's called the grid, but the idea is that this thing acts like say that you have like it's like a valve that you turn on with water on, like like a faucet, and that's like if like you can like control the flow of water with a valve, and this is kind of like that, to control the flow of electrons. That's why British people call it valves. I don't know why they call it that. Tubes are like way cooler. British people just they just don't get with the program. So what we have, so this is like amazing. Now, what's the whole point of this? What can we use this for? How is this useful? What's the amazing thing about this? What do you think? Like what can you do with this? What can you do with this? Okay. So XMDI suggests that you can change the direction with purpose. Well, yeah, that's true. Wait, what we got? Okay, so like, what's this? Hang on. Someone messaged me. That's nothing important. Well, I mean, probably. So, what we have, one thing that we can do, one of the things that, the most useful things here, what XMDI suggests is actually used in different kinds of tubes, like beam tetrodes, but we'll get to those later. So, okay. So the thing is that one of the things that we can do is that say that the anode. Now, in naming conventions, a lot of people like to call this part, like this part right here, this is the anode. They like to call it the plate. So we're going to use those terms interchangeably. We call this the plate. And the reason why we call it the plate is because of it's because in a tube, it's like a plate. So they call it the plate. So people call the anode the plate. Okay. So what happens here is that, let's say we charge the plate like a big voltage, like I don't know, like 100 volts. Boom, like 100 volts. Oh my God, 100 volts. Holy shit. So if it's charged up to 100 volts, we have one of the things that's going to happen is that the electrons on the cathode are going to look at this and be like, oh my God, look at that. It's so good. So they're going to be like going, bam, really, really, really out there. They really want that stuff. They love it. So what's going to happen here, if it's really big, on this output, the plate, because of, so the electron's going to flow this way. That means we're going to have big current going down. And like, well, so okay, so we have a big charge here, and that's kind of just useless on its own. And we have what we can do is we can introduce a signal here. Let's call it signal S. And the signal here may be like some kind of say it's not as strong as the 100 volts. Maybe it has a maximum amplitude of maybe 1 volt, so to speak. And when it goes in there, so let's say that the signal is a negative, so let's say it's like a sinusoid or something like that. And we're at the negative part. It will make the grid, we're calling this the grid, it will make the grid negatively charged. And when the grid is negatively charged, electrons, they do want to go to the plate. They want to go to the plate, but because the grid is negatively charged, they are impeded by the grid. And so one of the things that what will happen here is that the plate is not getting like we're not having current flowing. So so when current doesn't flow, well, actually, how does it getting look? Actually, hang on, let me check something. So, okay. So when it's negative here, this is negative. The grid is negative, and therefore the plate doesn't have electrons that's corrupting the voltage here or making the voltage lower. So we have a high voltage here, and because the electrons are still here, we have a negative voltage. So that would be where we have the plate voltage will be high, and the cathode voltage will be negative, and the signal voltage is actually -2. But when the signal voltage gets to like say the signal voltage gets to high, like it gets to the peak right here. If it gets high, then it allows current to flow. It allows current to flow from the plate to the cathode. And one of the things that does is that the electrons accumulate at the plate, and therefore, you guessed it, the voltage drops because we have a lot of electrons, or at least the positive voltage drops. So we have things go down, and the voltage at the cathode, well, it gets higher because it's losing electrons. And also the flow of current is the flow of positive charge towards the cathode. So because of this phenomena, one thing that we can have is that we can have like a signal where it's low. Like say we have right here, and the signal's low. Signal's low. Now this is the signal, and this is like say that this right here is the 0, the horizontal 0, like the X and the X-axis for the plate voltage, for the signal, and for the cathode voltage. So when it's low here, the cathode voltage will also be low, but the plate voltage will be high. And now, when the signal voltage gets high, plate voltage is low, the cathode voltage is high. So what we have essentially created is 2 signal followers. But these signal followers, like this guy right here, is a really high voltage. And this one right here is like another signal coming out, but polarized in opposite direction. It's phase shifted by like half a period. Yeah, that's what my notes said. I checked my notes to see if what I said was correct, and it looks like it is. So I remembered correctly. Nice. Okay. Now you guys know about triodes. Congratulations. Except that you don't know about triodes. Let me show you what you don't know. Oh, this was page 4. This is page 4. Page 5. So we have some problems here. I'm going to draw you a more accurate model of the tetra. I mean, not the tetra, the triode. So we have this here, this here. And we have this thing here. But so because this is a piece of, okay, so going back to the first thing that I told you guys about an electrode and the difference between like an anode and a cathode and a capacitor is basically what the purpose of this things are supposed to be. A capacitor still has 2 electrodes in it. Now, one of the things is that if we get 2 pieces of metal together that are charged, like positively charged and negatively charged, and there's some kind of dielectric in it, in this case, a vacuum, well, we still get some capacitance. And that's why this phenomena contributes to the reason why triodes are weak sauce. Oh, you want to see? Oh, sorry. You want to see a triode? Ah, a triode. Okay. He wants to see one. XMDI wants to see a triode. All right, give me a second. So one of the things about triodes, because of the capacitance, okay. So the thing about triodes is that they have the capacitance, which kind of hinders it in some applications. Can't use it in certain applications. And the other thing is that because of the triode is a very simple electrical component, and well, that has doesn't simple electrical components don't necessarily have inherent issues in them, but this one does for the kind of ambitions we want for its application. For example, that 100 volts I said to you, it may not, maybe it's not necessarily 100 volts. I'm not sure. It depends on what use. But the problem is that it cannot be used to like do a triode has limitations in how much amplification power it can have. So let me show you this actually. Get out of there. Okay, hang on. They'll come out. Okay, well, I guess I'll just push you out. All right, guys. There it is. The triode. Ooh, in all of its glory. So, let's see. So that, oh, come on, focus. There you go. So, you can see this piece of metal right here. That piece of metal right there, that is the anode. You can see that little piece of metal right there. That's the anode. And the reason why I call it the plate is because like everyone calls it the plate. That's why it's called the plate, because it looks like a plate. I'm going to show you a soft tech right now. Put you back. Don't these things like tend to roll away. Have this. Actually, hang on. So, take out the soft tech. Come on, focus. There you see it. There you go. So right, what you see right there are two plates. Those are two anodes. And the reason why there's two of them in there is because there are two tubes in this one tube. What I mean by that is that there are two of these electrical component configurations in this one tube. And I mean this. There's two of these in one tube. They're just they just have a different manufacturing kind of thing, like a different way of doing it. So this tube right here, I believe, is made in Slovakia, some small town in Slovakia. In the other one, the soft tech, it's made in Russia. So some American company, Electro Harmonix, they like somehow got the rights to the branding soft tech, because these used to be like manufactured by these are like these tubes are like Soviet tubes and stuff. So it's like, so they kept the name brand because it was what people were familiar with. A lot of history here. Okay, let me put these away so they don't. Oh, the name difference between them. Well, okay, so the real main difference. So okay, Okay, XMDI said the main difference. So, okay, so tubes are kind of like they're only used for like very certain things. They used to be like everywhere, like all over the place. But ever since like the '60s came about, and people a lot of appliances, home appliances and stuff, transitioned over to transistors, because transistors are just better. They're just better, unless like certain, but tubes they still have a purpose. So one of the things that these tubes are mainly used for, the reason like Electro Harmonics and JJ Electronics manufacture these tubes with essentially to market towards guitar players who put these things in their amplifiers. So guitarists like to do this because they like the way the guitar amplifier sounds with tubes. So guitar amplifiers with tubes sound different than guitar amplifiers with transistors, and that's one reason why these tubes, especially these kinds of tubes, persist. So this goes back to what I was saying about the amplification factor. But before I get to that, one of the main differences between these two tubes is essentially, besides the fact that one is made in Russia and the other one is made in Slovakia. Actually, it won't focus. There you go. So there we go. So the difference is that the plate on the Sovtek tube is longer than the plate on the JJ. So one of the things that the main difference in the performance is that these tubes, believe it or not, are microphonic. That simply means that the amount of frequency that these are subjected to, they react in a certain way. So like an object has a natural harmonic to it, that if it's the frequency, if the fundamental frequency that passes through an object's fundamental frequency or fundamental harmonic, I think that's what that is, it will make that object react and absorb a lot of energy from that frequency wave. So for example, this tube right here has a smaller plate. So essentially with a smaller plate, one of the things that you have is a higher fundamental frequency. So let's see. So you have like a big long plate and you have a smaller plate. So one of the things is that this here has a bigger harmonic fundamental frequency. I don't know if it's a harmonic. I don't know the H. We're going to leave the H. This has a lower fundamental frequency response. So effectively, this plate will absorb lower frequencies. Like when the certain frequency hits it, it will like absorb it and react to it, and it is not pleasant. On my guitar amp, one of the tubes is microphonic, and so if I play like a G2 on my guitar, it just the amplifier just goes crazy, and it's like insane. I just don't like it. I'm like, what can I do about this? Well, I mean, the way you fix it is you put something on the tube to you could put something on the tube to change its frequency and change how it reacts. But there's a problem, and that relates to the problem of triodes. Triodes have a problem, and here's the problem. So before I introduce that problem, I need to tell you something. I need to tell you something really important. So you saw in the previous sheet, the paper, that we have an input voltage signal, and we have a voltage plate and a voltage on the cathode, and they have like they follow the voltage signal, but they're at higher amplitudes. Now, so let's put it like this. So if we have V of the signal, that's the denominator of, say, the V of the cathode, or maybe or it could be the V of the plate. Maybe the V of the plate. Let's just put the V of the plate. Yeah, let's put the V of the plate. Why not? So if you do the voltage of the plate divided by the voltage of the signal, the input signal, or it could be the voltage of the grid, this ratio is known as the amplification the amplification factor. The amplification factor. I think that's correct. So we're going to denote it as mu. And this is the amplification factor. So one thing that we want is like in an amplification or like in a radio, we want the signal to be strong enough to drive a speaker. So like a speaker, we have a speaker here and we have wires around the speaker, and we want these wires right here, and they are actually, is that how it is? Yeah, I think that's how it is. So what we want is that this speaker, we want the signal getting to the speaker to be so large that it makes the speaker make sound. That's how you're hearing me. And one of the issues is that we need the signal to be kind of big, like really big, like 200 volts or maybe higher than that. Probably. Let me think. Okay, so yeah, we want a big signal compared to the input signal. So this brings some issues. The triode has a problem. The triode kind of sucks. That's the problem. It's like awful. It's like kind of pathetic, really. So what do you think the amplification factor is on these triodes? What do you think it is? Tell me. Let me put these up. It says electron tube. No, it's not that big. It's not that big. So the answer is that it's 100. That's pretty big. But you know what? You can't go bigger than that. If you try, you're gonna have problems. You're gonna have problems. So I'll tell you the problems. So the problem like tetrodes have not a very high okay. So one thing we want to do is we want the signal to be reproduced authentically. We don't want distortion. like it would sound terrible. You know, AM radio. Well, yeah, there you go. Well, but worse. Like when I go and I clip the microphone, there's distortion, and that sounds terrible. But you know what? It's like there's a way to fix that. So so here's some downsides. So one of the downsides is that this capacitance is about 3.8 picofarads. And that might be, oh, so what? It's pretty small, right? Yeah. I don't think so. So the thing is that these are good for like guitar amplifiers, but they're terrible for like radio frequency applications, because I don't know if you noticed, but radio frequencies are high and guitar signals, they're not that high. So do you guys remember how like you guys I'm sure you guys took like linear time invariant systems, right? So if you guys took that class, you would know that one of the like physical phenomena of an AC circuit is that it like passes through like capacitance. Well, it's like, actually no. So okay. So one of the things is that when like an AC circuit like passes like okay, so you know, let's say you have a capacitor. You have a capacitor, and the capacitor takes time to charge. It needs time to charge. And the thing is that on the tube, on our tube configuration, like we want this to be an open circuit. So to have it be an open circuit, we don't want this to connect, basically. But there's a problem. So say you have an AC circuit, but like the AC is like really low. So the AC is essentially quickly saying it's like an up and down voltage from V plus to V minus. Actually, I don't think you can see that. V plus to V minus. And one of the things is that it's going to like we don't want it to charge the capacitor totally, and it won't. But if the signal gets if the AC gets really, really high, then it will go right through the capacitor. So effectively, this will be like almost like a connected circuit. And when that happens, this thing it just doesn't matter anymore. It doesn't matter. So it's kind of like acting as like a high pass filter, but we kind of don't want it to we don't want to make a high pass filter or utilize a high pass filter. We want to make an amplification circuit. So the thing is that if we use a really big signal, really like high frequency signal, like if Vs is like really, really high, then it just doesn't matter. Like the circuit, like this doesn't matter. It doesn't work as we want. So that's like a really big downside. That capacitance right there really, really throws a wrench in some of the applications that we would like. See what my notes say. So here's the other thing, the other problem with the triode. So in the plate. So like we have electrons. We have little electrons, and they go right through the plate when right through the grid when the grid allows it, and they go to the plate, and they're happy, yay, happy. But some of them are not. So they impact the plate. And when electrons impact the plate, what happens? Some electrons are knocked off. Some electrons get knocked off, and they go out, and they go all over. Now, a good number of them are going to go back to the plate. And, that's what that's okay. That's fine. I mean, it makes it imperfect, but it's still like doing what we would like. But some electrons can accumulate on the grid. And that's a problem. So you guys know that if you have a high plate voltage, you encourage electrons to go from the cathode to the anode. And that's really, really cool for like doing that. So what happens if you make the voltage too high? Let's say you make it really, really big. What happens? I just talked about all these electrons bumping off. So like, let's say you take that to extreme, what happens? Okay, so you run out of ink drawing the electrons that left. Yeah, basically. So one of the problems is that the electrons, like if VP gets too high, well, I'm gonna have to write all the E's that bounce off. So what that happens is that the grid gets so they will go. The kinetic force of these electrons it's become so strong. The FK sub E gets so strong that it knocks so many electrons off the plate, and they get tangled up in the grid. And therefore, the grid doesn't become a good valve, as the British would like to say. And that's the problem with triodes. Triodes just suck. But they're pretty good for phase inverters. Yeah. Triodes are fine for phase inverters because you're not really amplifying a lot. You're just kind of flipping it, because like you saw in that actually, where is it? Oh shoot. Yeah, because you saw in this thing that it inverts the signal. So that you can use that. You can use this in another part of the amplification circuit. So triodes good for that, but because of this, triodes kind of suck. So, guys, I would like to ask you, how can we solve this problem? Do you have an idea? Can you figure it out? This thing that I'm about to say, that I'm about to introduce to you, is like, I looked it up, and I couldn't necessarily conclude who invented this upcoming thing. apparently a lot of people figured it out at the same time, or maybe some people are stealing other ideas, or maybe people the people that wrote history don't know what they're doing. So let's see if you can figure it out. So what can you do to solve this problem of F sub K sub electrons? Come on, think about it. Think about it. Some nutcase with that looking at diodes put in like a syringe, like XMDI said. They put in a syringe. That syringe of metal to mess up with the electrons. So what do you do? So you're looking at this problem and you're like, your boss is howling at you, solve this problem, and you're like, oh God, what do I do? What do I do? You know what I do when I'm in such ridiculous circumstances? I brute force it. I always brute force my problems. Everything. I brute force everything. So just brute force it. So brute force the thinking. Do a brute force thinking method, and you will be able to figure out the solution to this, right? Come on, just do it. You know what to do. I mean, you're smart. You guys are smart. You know what's what. All right. Okay. If you guys okay. XDMI, did you figure something out? Okay. How about I'll just tell you what it is. I'll just tell it to you. So we come across this problem of FKE, and what's the problem? What's the solution? Here's the solution. Add another control grid. Boom. So here's what we do. Here we are. We have the anode and we have the cathode. Anode and cathode. We put the grid, the signal grid, we're going to call it G1. And then, we put another grid. G2. Oh, and we have it. Oh, this is it. We did it. This is called the tetrode. I don't know who made it. And you know what? I looked it up, and I don't believe that's the person who made it. I mean, I thought maybe some Japanese guy made it, but apparently it might have been some English guy or some American. I think what's that company? British people invented the pentode, but that's for another story. So here's the deal. Because of this new geometry, the capacitance right here is like really, really small now. See, 1, 2, 3, 4, 7e negative 4 picofarads. Yeah, 7e negative 4 picofarad. This thing is kick ass. It's so small. So it's like we can have big inputs signals. So this is called, this G2, we call this the control grid. G1 is the control grid. G2 is the screen grid. So G2 is essentially like G2 is charged positively. It's charged positive, almost as positive as the plate voltage. So G2 is slightly less than the plate voltage. And the reason why is because what we do is that we create like when an electron strikes the plate and knocks another electron off, that electron has to decide, what am I going to do? Am I going to go to G2, or am I going to go to the plate? The plate's higher, so I like that. That's kind of what's going to happen. So because of this, we can have a really big amplification factor. We can have an amplification factor of 600. Dang, it's so much better. So, well, I guess I'm kind of bad at this whole thingy. But how should I say this? So one of the things that we like about the screen grid is that it allows for the voltage on the plate voltage to be extremely high. But we have a problem. So one of the issues is that some electrons will still want to go to the screen grid. Let's say that the voltage of the plate is 400 volts, and the screen grid is 380. That's still 380. That's still pretty high. You don't want it to be by the way, you can't make this so low. If you make it low, you might, no. Well, because so the grid, the G2 is direct current. So we're not going to have noise or anything like that from external AC interference. But so because we can raise the voltage of the plate voltage so high now, why wouldn't we do it? We're going to do it. And it goes back to the problem before. And the problem is that voltage, not voltage, force of the kinetic energy of the electrons leaving the cathode is now super high. And so more electrons are knocked off. And, well, when you get electrons knocking off, some of them are going to be at the screen grid. And what happens? You know what happens when you have electrons going to the electrons? We want electrons to go to the plate, but some electrons are going to go to the screen grid. So we're going to have current flowing in the opposite direction of where we want it to go, and this creates a phenomenon known as negative resistance. And when I saw that, I was like, what the heck? My gosh. So the thing is we don't want negative resistance. That's bad. Okay. That's bad. So now we have the plate. We have the plate and the screen grid competing for electrons now. And that creates instability. And we get a phenomenon known as parasitic oscillation. Now, this can be useful, but for certain applications. So, but for in guitar amplifier circuits, tetrodes are a big no-no. It's a big no-no. So now, I guess there's some more I could say, but I think we're pretty good. So this phenomena where electrons get knocked off and they don't this whole phenomena where electrons get knocked off is called secondary emission, because the primary emission is from the cathode. So with secondary emission, how do we solve the secondary emission problem? XMDI. How do we solve this problem? Now, come on, you got to brute force it. Think about it. That's how I solve my problems. I just brute force everything. So how do you solve this problem? How do you solve the problem of secondary emission? Come on. You're smart, right? You can do it. You know the answer. You already know it. Just do it. Just tell me the answer. Where's my phone? Okay, so you said something. On cars, they reduce emissions with a catalytic converter. They reduce emissions with a catalytic converter. Well, I don't know what that is. Actually, look it up. Catalytic converter. Catalytic converter is exhaust emission control device, convert toxic gas pollutants to an exhaust to less toxic pollutants. No. All right, I'll just tell you. So we at the guys at Mullard, yeah, little guys at a company called Mullard. I think it's Mullard, yeah. Some British. They're British. So they're like, oh, we have this problem. What do we do? How do we solve this problem? No. This is how they solve the problem. You're going to be like, oh boy, obviously that was the answer. That was obviously the answer. So if you look at the contacts on this tube, I don't know if you can tell, but you can tell like in the center of the tube, in the center of the plates is the cathode, and it emits outward to the plate, which surrounds the metal. This is the metal encasing is the plate. That's why it's called the plate. So I don't know if you can tell, but here's what they did. They added another grid. They added another grid. Oh my God, they did it. They did it. They added another grid. So here's what it looks like. Here's your 1 grid. Here's your 2 grid. And here's your 3rd grid. Boom. This is called the pentode. And that's it. And this is like this thing right here. Like, my God, this thing is so good. It's so good. It's like amazing. It's like incredible. It's like the American companies were so pissed off that they couldn't figure this out. Like RCA or Raytheon, they were like beating themselves up because they couldn't figure this out. Because all the guys at Mullard, all they did just added another grid, and then boom! Like, why didn't anyone think of that before? I mean, the guy who made the Tetrode, he just added another grid, and then boom! And just brute forced it. I mean, like, God, what happened to brute forcing? All right, that's it. I'm done. You want to say something? You have something to say? I have a new idea for a hexo tube. What's the idea? What's the idea? What's the idea? Come on, you better tell me. Come on. Okay, so all right. So, okay, I forgot to mention some awesome things about the Tetrode. Not the Tetrode, the Triode. The Triode has some good shit on it. So, the Triode has, let's see. The Triode has a low distortion, which is good. 3rd order harmonics. So, this is like an acoustics engineering kind of problem. Also electrical engineering, but I don't know. So, I don't know too much about acoustics. Now, there's a thing that says because of the low distortion, we don't need a negative feedback loop to adjust it and make some good modifications to it. Which, it's basically we don't have to have a more complicated circuit doing more complicated stuff. And it's like it has high fidelity, and that's pretty cool. So here's some of the duo triodes that I showed you earlier, but different like names for them. So what I showed you earlier was the 12AX7, and its amplification factor is 100. And here's some other tubes with not so high amplification factors. And the thing is that these tubes are like ancient. They're like we don't really use a lot of them anymore. But some of these tubes are like good for like phase inversion because we don't necessarily need that high like the high amplification factor is useful for like if we're running high voltage on it. But since like for some of these lower ones, you don't need as high voltage, and especially for a phase inverter, you don't need high voltage. You could probably use maybe a 12AU7. I think that I don't know if that's the right amplification factor for an AU7. I might need to check my sources again. So it looks like XMDI said another grid. You know what? My God, it took you this long to catch on. Actually, let's see. I wonder is there actually is a hexo? What the heck's a hexode? I wonder, is that a thing? So here's the thing. Yeah, that is a thing. So here's the thing, XMDI. So the thing about with that, the hexode, says hexode, mixer frequency charger valve that was developed after the heptode was a more efficient thingamabob. It had triode, hexo, and now we have a common cathode. All right. So when it comes to like, okay, so the next step isn't it's not a hexode. The next step, so I like your thinking, but that's not how they solve this problem. The guys in the Americans, when they saw the pentode, they were freaking out, but I think one of them solved it. So that's called the beam tetrode. The beam tetrode, like, that's like an amazing tube. It's actually better than pentode, but that's for like another time. All right, any questions? You guys love this stuff, or you guys are done, or what's up? What's going down? Let's put this on. Any questions? Anyone want any questions? Questions here. Questions now. Forever hold your peace. Now this here is actually, I think this might have been pulled from like a television or something. This one is actually an old one, really old one. So this one, let's get it to focus. Get it to focus. There you go. So this is kind of like, looks like the Sovtech. This was pulled out probably I don't know, so maybe the radio or something. So if you look at the leads, you can tell that this one has been well used, and yet it has. This is a used tube. It's not like a new one like the JJ or the Sovtech was. Now, so like the tetrodes, since they're not driven, so since their amplification factor isn't as high as like a pentode or beam tetrode, the voltage used on these things isn't as high. So therefore, these things actually last quite a bit longer, possibly 10,000 operating hours. This one is probably halfway through. And I don't know if you can see the logo, but it says this is actually a USA made tube. Most of them are made in like either, like there's like I think there are 4 factories left in the world that make tubes. So you said hook up the anode and the cathode of the Sovtech to a 120 VAC. Yeah, in your dreams. So, no, I'm not doing that. The Sovtech is not designed to handle that much voltage. If I get like a beam tetrode or like a beam tetrode or maybe a pentode, maybe even that, you could probably, nothing would happen. Because it would be like an open circuit, because the grid doesn't have anything happen. Well, actually, let's see, in the grid. Well, oh shit. Yeah, don't do that. 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 Okay, don't do that. All right. I'm done. Bye bye. Farewell.